Hello Design 1. Today we will be supplementing your understanding of fatigue and endurance limit. At this point, you will have become familiar with component failures in axial, bending, and torsional loads. However, fatigue is a new but essential mode of failure. Essentially, fatigue is the process by which a component fails due to cyclic loading. A cycle is the process of loading and unloading stress on a component. As the number of cycles increases, the failure stress will decrease. Therefore, the part may fail well below the yield stress of the material if the part has undergone many cycles. The table shows that the failure stress tapers off and approaches a constant value as the number of cycles approaches infinity. The stress at which the number of cycles approaches infinity is known as the endurance limit. If the component's max stress is below the endurance limit, it is expected to survive an infinite number of load cycles. Determining the endurance limit is typically done empirically. However, you can approximate the endurance limit of a given component by multiplying a number of scaling factors by the endurance limit of a test specimen. Here we will go over each scaling factor and how to calculate it. The first parameter is the endurance limit of a test specimen. You can use the table below to calculate its value based on the ultimate tensile stress of the material. The endurance limit of a test specimen is half the ultimate tensile stress, up to a maximum value of 100 kSi or 700 megapascals. Next is the surface modification factor K sub A. This captures the effect of imperfections on the surface, which decrease the strength of the component. Based on the manufacturing processes used during fabrication, you can refer to the below table to determine the coefficients required for the following equation. The size modification factor K sub B accounts for differences in sizes of the component. If it undergoes axial loading, let K sub B equal 1. For bending and torsional loads, use the diameter of the component to calculate K sub B. These equations apply to circular components and are only valid for diameters between 0.11 and 10 inches. The load modification factor K sub C accounts for differences in the types of loads that are applied. Using the below table, you can see that K sub C equals 1 for bending, 0.85 for axial, and 0.59 for torsional loads. K sub D is the temperature modification factor. The simplest way to calculate K sub D is to find the ratio of ST to SRT, where ST is the tensile strength at a given temperature and SRT is the tensile strength at room temperature. Using the table below, find the ratio of ST to SRT for the operating temperature of the component. K sub D is approximately equivalent to this ratio. However, an alternative method is to use the below equation using the operating temperature T sub F. The reliability factor K sub E captures the desired precision of the endurance limit. You can set the percentage at which you are confident that the endurance limit is correct, and then use the below table to calculate the reliability factor K sub E. Lastly, the miscellaneous effects modification factor K sub F accounts for any additional characteristics of the component that are not captured by the previous scaling factors. Since this is such a broad category, there is no equation or table available to determine it directly. Unless otherwise stated, assume that K sub F equals 1. If you wish to include this scaling factor, you will have to consult additional resources. This concludes our review of fatigue and endurance limit. We will be attaching this document in handout form for your future reference. We hope that you have found this video useful.